Hello again everybody, this is Zap Andersson from Autodesk, and this is my lesson number 2 in writing your own OSL shaders. Today we're going to talk about something as exciting as data types and globals. Trust me, it will be kind of exciting eventually. I'm kind of expecting you guys to have sort of seen lesson number 1 semi-recently, or at least watched it, so I will not repeat myself that much. That's what YouTube is for. So I'm going to go straight into this. And this is pretty much one take and a little rambly. I might make some mistakes and stuff. Please bear with me in my stumbling over my own tongue. And here we go. In OSL we have a few specific data types you don't find in languages that don't deal with shading. And the most obvious one is obviously color. We're going to be dealing a lot with color because that's the whole point, generating pretty colors. Now, colors in OSL do not have an alpha, they are RGB colors. And the values are in the 0 to 1 range, 0 being black and 1 being white. We do not deal with the 0 to 55 thing that you see in many other color things, because that really has to do with final pixel colors, like video memory bytes. Although I admit Max in some places asks for color in 0 to 55, where they really should be asking in a 0 to 1 range, and that's things we probably should fix someday. Points is a type that we use to encode a position in space, some XYZ coordinate of somewhere in space. And vectors are used to encode a direction, something pointing in a particular direction. Vectors don't have a position, they just have a direction. And normals is a special case of vectors, vectors that are perpendicular to a surface. Now, the difference between these types only matters when you do certain kind of math to them, specifically transformations. Then which type you use is important. And if you don't use any of that math, they're actually interchangeable. I've seen people basically use vector for everything, and as long as you're just dealing with it as if it's a container of 3 numbers, heck, you can even throw colors into vectors, and OSL will really don't care that much. But it's a really good practice to, if not just for the sake of beauty of the code and the explanatory power of reading the code, to use the right type. And when we get to transformations, we'll see it actually matters quite a great deal which type you chose. So pick the right one. Now, these types are 3-valued types. They had a red, green, and blue value, or an XYZ for the point vector and normals. Now, in OSL, to access one of the components, you, and I must say unfortunately, use a bracket syntax. Those who've been programming in other languages recognize this as accessing something in an array. So it thinks about the type as something with an array with 3 values. And since programmers are programmers, of course we start counting at 0. So the first item in the array is numbered 0, the second is numbered 1, and the third is numbered 2. Obviously, because we're programmers. Sadly, most other languages use a syntax where you say blah.r to get the red component. Unfortunately, however nice and readable that is, that's not what we do in OSL. We have to do blah bracket 0 bracket to get the red component. Here's some examples. We declare a color variable, we call it something, and we assign it to the color value 1.50, which is 100% red, 50% green, and no blue. We then declare a float variable named red that we assign to something bracket 0. Bracket 0 is the first component. Yes, programmers start counting at 0, so that means red. We can also use that on the other side of the equal sign. So here we're assigning to something 1, which is then the green component. We assign the value 0.25. So it used to be 0.5, where from this line on we actually changed that to 0.25. Here we're creating a vector, we call it up, of the value 001, because everybody knows that Z is up. To underline that more, we create a float variable called Z is up that we set to the value of up bracket 2, which means the Z value. So this is how you actually access the individual components of these things. Next, we have something called globals in OSL. Globals, also known as global variables, is the thing that in the language they just exist. There's nothing you have to declare. These variables are just there. Actually, if you try to declare a point named P, you most likely will get an error messages because that's basically a reserved name. And the most important globals are indeed the point P, which is the shading point, the vector I, the normal, the geometric normal called NG, and U and V, which is the default 2D surface texture coordinates. And in 3ds Max that maps to map channel 1. To show how this in more detail works, I set up this little image. Imagine you're rendering from a camera and you're shooting a ray through a pixel onto the surface of this sphere. It's a fairly low poly sphere, so the line here is supposed to be the actual polygon, and the dotted line is kind of the way the sphere looks with the smoothed normal. So the ray hits the surface at the point P. Now this point is by default in Max in world space, so it's a coordinate in world space defining where the ray hit the object. The second one, I, is the incident ray direction. It's a vector, so it's a direction. It's the direction from the camera towards the point, not the other way around. Some other shading system use a vector that points towards the camera, but here it's coming from the camera towards the shaded point. Then we have the normal. And the normal is of course very important in shading. It's the smoothed normal, the shading normal, so it is perpendicular to our hypothetical round surface, the dotted line here, as contrasted to the geometric normal called NG, which is actually the normal of the face we hit. If we don't have smooth shading, N and NG are the same if it's flat surfaces, but if there's smoothed surfaces, N is the one you use for shading, but NG contains information of the actual flat polygon we're hitting. And then of course we have UV, which is the U and the V coordinate of the default, in Max, the default map channel number 1. Now, these all come in some kind of coordinate space, and by default they are in a coordinate space that is in OSL known as common. What common means is technically different per renderer, although in almost every renderer that actually exists, it's the world space. But to be really sure, we should actually write like this. We declare a point called world point that we set to transform world within quotes of P. This will take the point P, convert it to world space, and drop it in our variable world point. So by writing this, we know world point will be in world space. Now, since in Max the P is already in world space, this will actually do nothing. It will be exactly the same as just saying point world point P. But it's technically safer to write your code like this, because if your code ever ends up in a render where P is in some other coordinate space, this will then be in world space. But in Max, you technically don't need this. If you want the point in object space, though, you absolutely need to write this, because P was in world space, and this line transform object within quotes will convert it into object space. And if you need the normal in object space, you just do the same. And it automatically, by the fact of normal being type of normal, it will do a slightly different kind of transformation. We'll talk more about that in the next lesson. Now time to play with this a little. So when we left off lesson 1, we were basically at this point. We had written this amazing little thing called My First Shader. The only thing it did was mix two colors. So 0 it gave color A, and 1 it gave color B, and anything above 1 or below 0 was working correctly and not making any strange math. Now this is of course not very interesting shaders because it really doesn't do much. It just takes inputs and works on them. So we're going to play with it a little and add some code to make it do slightly more interesting stuff. So first thing I'm going to do is to look at this F that right now comes in from the outside from this spinner. And I'm going to do a slightly different F. And I'm going to create my own variable, and I'm going to call it F in lowercase. And I'm going to assign it to the value of U. U, if you remember, is one of the globals. You notice it lights up in a different color to indicate it's one of the globals. And I'm going to switch this uppercase F to the lowercase f. Variable names are case sensitive. So the uppercase f and the lowercase f is different variables. This is really important. You can't be sloppy with upper and lowercase because that will not work correctly. If I now compile this, you will see I have going from red to green because this UV preview has the U coordinate going from left to right. I have this going now from red to green across the object. If I launch my rendering here, we'll see the same effect where the red to green is happening on my object from left to right, right here. Now, you might wonder why I made the lowercase f. Well, I have a little bit of a convention when I write code. You've seen in many of my examples I wrote stuff with a lot of uppercase. But what I tend to do, although I admit I'm not even consistent myself, is that parameters, I give them uppercase name because it's nicer to read them when it shows up in the user interface and make sure they have, you know, the first letter is uppercase. Basically looks better. But variables within my code that are not parameters, I kind of tend to make lowercase. This is not a rule, and you'll see me being consistent with it 30 seconds from now, but it's kind of what I do, and it's kind of a choice I've made for no particular reason at all. So we have now made showing the U coordinate. If we change this to V, we'll see showing the V coordinate instead, going from red to green along the V coordinate. We can also test with the P, the point. If I try to set it to P, well, I will get an error because you cannot assign a point value, which is a 3-valued thing, to a float variable. So I will have to use the component syntax to pick one of the components. 0, as we recall, was the first component, the X value, because programmers count from, you know, programmers are weird and start counting at 0. And here we see what happened now. It just went from green to red. Yeah, because this scene is kind of big. So if I zoom in a lot, we might see our little fade here from red to green. But it goes really quickly. So to make it go less quickly, let's divide this by, say, 100. And there we see we have our little smooth gradient. Maybe I should do 50 instead. We see it a little more quickly. So this is now the X coordinate, but it's the X coordinate in world space. So if I grab my teapot and move it out, it becomes greener, and as I move the teapot across here, it becomes red. If I try to extract the Y component, that would be 1 here, you will see the same effect in the other direction. And of course, if I do 2, it will be the Z coordinate. So now I can sink my teapots down and make them red, or up and make them green. Okay, so let's do this. We create a new point variable. We call it P&T, and we set it equal to P at first, and just change this one P&T to P&T. This will of course do exactly the same as we just did, so there's no difference. We've just made a new variable, but I'm going to do transform object P. So point will now be the object space version of P, and we're going to use that instead. What does this look like? Well, it looks kind of similar, except when I move this teapot, you see it's still green. it doesn't change. If I move this back to my x coordinate, it's perhaps more obvious even that you see the teapot is basically half red and half green, and this doesn't change. Even if I start rotating the teapots or doing things like that, it sticks to the object. Object space tags along with the object. I change this to the y coordinate, or I change it back to the z coordinate. You'll see it tags along with the object. But as shown before, writing world here gives me back to the situation where sinking the teapot down makes it red, like this. And as I said, in max, P was already in world, so this doesn't really do much. But we can try a few other interesting. There's a screen coordinate space. The screen coordinate space goes from 0 to 1, so maybe I need to remove my division by 50 here. There we go. So it goes from 0 to 1, and we wonder why is everything green? Well, I'm picking the z coordinate. The screen coordinate space doesn't have a z coordinate, so let's take x. And now we see the screen coordinate space. It has the 0 coordinate in the middle, 1 is over on the right, -1 is on the left. So that's why everything is kind of red on the left side, and you have your green gradient on the right side of the screen. There's a different coordinate space called NDC, a normalized device coordinate. That has 0 coordinate on the left, upper left corner, and 1 is on the right. So it's almost the same as screen, but the difference is where the 0 point is. In NDC it's upper left, in screen it's actually in the center. And then of course we have raster. Raster is in pixels. So the values will of course be huge, starting 0, 0 here, and 1 is the next pixel going to, well, say 600 pixels or whatever. So clearly, to get this back in our 0 to 1 range, we need to divide it again. So let's divide it by 500, and we'll see we have our gradient back. And actually, raster is exactly the same as the NDC coordinate space multiplied by the screen resolution. So it's in pixels. NDC is 0 to 1 across the screen. And of course we can try to use the y coordinate instead. So we have red to green from top to bottom of the screen instead, like this. Very nice. Okay, that was those coordinate spaces. But let's go back to texturing in UV case. So you say at f equals u again. We can forget about this line for now. We might use it later, so I will keep it around for the moment. But we say f equals u, so we're back to the case where we have our gradient going from left to right here on this box. But now if we look at our teapot carefully, we notice one interesting thing, and that is the teapot is going from red to green, and then it kind of stays green. Then it goes from red to green and stays green. This is actually because the teapot primitive in max is a bit interesting in that the UV space on it goes from 0 to 2, and then back from 0 to 2 again. So how do we use that when it's kind of continuously growing, but we might want to make something that repeats? We want to make something that goes from 0 to 1 and 0 to 1 and 0 to 1, etc. Well, there's a few ways we can try to do that. So let me think. What's a way to basically get the decimal portion? We basically want to get rid of the integer value. So when we go from 0 to 0.999, we want 0.999, but when we hit 1, we actually kind of want to start from 0 again, and we go to 1.1, we're going to treat it as if it was 0.1. Well, one way to try to do this is to use the modulo, the remainder of the division, which is also called modulo. And there's a function called fmod to do that. So we say fmod with 1. This will basically take the remainder of the division. And now we see we got red to green and red to green and red to green and red to green, which is kind of what we expected. So this might be useful someday. Many other languages, shading language, ironically have a specific function for this. It's called Fraccked. It basically takes the fractional the fractional side of something, basically tears off the integer and just leaves the decimals. As we go from 0 to 1, it's basically just the decimals, but as we go from 1 to 2, it's also just the decimals. But OSL doesn't have a Fraccked. Dagnabbit, that's a little strange, I must admit. But since we can write our own function, let's make one. Float, Fraccked, and we have a float coming in, just call it in. And we do this little brackets, and we say return, and I paste back what we had, which was the fmod from u with the remainder of the division with 1. So let's test if this works. It works the same now. It's as if when we had the code down here. I'm going to make my code window a little bigger so we see more code. So really nothing changed right now. But what about if we, instead of using this u coordinate, we go back to using this point variable, the first coordinate, and we say world. Oh yeah, this is wrong. This should say in, obviously. There we go. I was a little surprised there for a second. You see? Mistakes and null. Perfect. So now we see a bunch of things. First of all, we have some little stripes here, kinda, but they're really tiny. So let's put in a division by, I don't know, 20 or something. There we go. Now we at least see our little gradients, but something went wrong. Everything left of this line is red. Well, it so happens that this line is where 0 is. The 0 coordinate in this scene happens to be here somewhere. So these are all negative values in world space. And it turns out the way the remainder of the division works, that turns out not to be what we want. Because the remainder of the division for negative 0.2 is negative 0.2. How do we fix that? Well, we can use something called the absolute value. And there's a function for that. So we say abs and put the rest here within brackets. So we take the absolute value of our division, remainder of the division. Yes, that fixes it. Now I have stripes, right? Well, not exactly. You notice that one of the stripes is different. It turns out these are going from red to green, red to green, red to green, but on this side it's going from green to red. And here's the 0 line. Yeah, because from the 0 line, your remainder will be growing in both this direction and this direction. When we did abs, abs basically throws away the negative sign. So this is wrong. We actually implemented our Fraccked incorrectly. What we want in this case is to have something that repeats from left to right, regardless if it's negative, regardless where we are on the whole coordinate line. As long as we're going from basically a lower value to higher value, it should grow, then drop back again, and grow again. Well, I won't bore you with every detail, but the way we can fix it is to say that we start with the in value minus floor in. So what does floor mean? Floor gives you, it rounds a value down, and down is defined as towards negative infinity. So floor of 0.1 is 0. Floor of 0.9 is also 0. Floor of 1.1 is 1. So we're moving down to the nearest lower integer. But the floor of negative 0.1 is negative 1. So we're moving down 1 the whole time towards negative 0, which effectively means when we do this, we get the right result. We go from red to green, red to green, red to green, always doing ramps from red to green like this. But by the way, I'm getting really tired of red to green. Let's switch to blue and yellow because those colors hurt my eyes. There we go. Much prettier. Now, we mustn't forget that this shader that we're writing takes other shaders as input. So we can just as well take our candy and our noise and connect them, and we get this fantastic, you know, candy to noise, candy to noise, candy to noise instead. Just so we don't forget, this is all part of a greater thing that we're doing. Now I'm going to do something that first you're going to wonder, why am I doing this? I'm going to make a new function, and I'm going to call this function my function. And we'll have an input float, we call it in, and what this function is going to do is going to simply call fract of in, and return fract of in. And I'm going to go down here and I am going to change this to, instead of calling fract, calling my function. And you're going to wonder, why am I doing this? Well, it will be clear in a moment, because obviously this does nothing different than what we just had, because we were just embedding this function in that function. But I want to start playing with maybe doing other things than using fract, but fract might become useful in the future, so I'm kind of keeping this around. So that's what I'm doing. So, for instance, what I want to try to do is to make a shader that makes stripes of some kind. These are kind of stripes, but I don't want this sharp edge, so I want something that goes back and forth and somehow. And immediately, as a computer graphics nerd, you think, oh, a sine curve. Sine curves are nice and wavy and stuff, so let's use the sine function and see what happens. Well, we got some kind of stripes, but the size is kind of wrong. And if you think about it, and if you remember, the sine curve goes, you know, up and down around 360 degrees. But this function takes the value in radians and not degrees. Well, we can do it with using the radians helper function and 360 times the input value. So this gives us those stripes. But if you remember some high school math, you probably kind of happen to know that 360 degrees is 2 times pi, which then is 6 times 6.28. So we can just as well write this as 6 times 28, because pi is 3.14, right? So this does exactly the same thing. I'm a big fan of doing things that do exactly the same thing, but you will see why this makes sense. So now I have something that makes little stripes. That's nice. Let's try to make them in the other direction. Oh, look, I can make the stripes in that direction. Oh, let's object space stripe. There we go. So these stripes are now sticking to the object. As you see, I rotate it. The stripes are sticking. When we were in world space before, the stripes would not be sticking to the object. They will be sticking to the space, and my object is kind of moving through the space. Now, the sine curve, as you might recall, goes from 0 to +1, back to 0, and down to -1. And that's why our stripes here are kind of mostly blue, and are fade into yellow and fade out, but are flat blue, because this is where all the negative stuff is going on. And I kind of don't want to use the negative side of it, so I'm going to use the abs thing we talked about, which throws away the sign, and try this. And now we effectively get a shader that makes nice little blue stripes. That's kind of nifty. We have a blue stripe shader, and they're a little smooth and faded, and this could be the beginning of something that could actually be useful. Okay, so what can we do with blue stripes? Well, so what we've done so far, well, there's stripes, but it's incredibly one-dimensional. We're only working along one axis. So let's try to do something, we were on the x-axis, and we can be on the y-axis, and we can be on the z-axis, but what if we want to make it on two axes at the same time? So we want to use this function again, but call it for the other. So let's say if we add the x and y. Okay, that was kind of interesting, but we're adding them together, so we're getting values that will exceed 1. So what happens if we subtract them? Let's try that. Okay, that was interesting. Okay, might be useful. It kind of looks a little bit like, carbon fiber or something. But let's multiply them. Ooh. We had really nice blue stripes. Now we have a grid of kind of blue glowy lines. That's interesting. It's of course right now, as we see, in world space still, because that's where we last left it. Let's look at it in object space, like this. Again, now our blue grid is nicely following the object, as one would want. It's a nice grid we have. If we play with this value, we see that we got a really small one. Okay, divide by 30. It's interesting, one would think that multiplying would scale something up, but what really happens is that it's the coordinate which is moving really quickly. This is several hundred across, and we're in world space. And each of these squares are 0 to 1. So to make the square be bigger, we need to divide it with the greater number. Now, of course, we don't want to type stuff into the shader all the time. So what we want to do is to make this a parameter. So let's call it scale. And we're not using this f anymore, so let's call it that scale. And as you see, I write this with uppercase, and I make this, 50 or something. And now I can tweak this value, and we can scale up and down our little grid. That's really fun stuff. So let's make a new point that we call UV, and that point is U and V and 0. And instead of this transform object P stuff, now we put in our UV point. And we try that. Everything turned blue because, of course, UV is only changing really slowly from 0 to 1. So our scale will have to change to something less than 1. So maybe say 0.3, whatever, like this. Now we have our grid back. And now you see we have it in UV space. So it's wrapped along the teapots. And it behaves as regular 2D texture mapping would do. So now we made a nice 2D texture grid, blue and yellow grid shader. So we're getting somewhere. We're writing our first almost sort of kind of nearly useful shader. Isn't it amazing? I think we're doing good. But here's the thing though. Here's the thing. We're doing all this UV and all this kind of stuff inside our shader. This is really stuff that actually should be coming from the outside. So the simplest case we can do is this. As you might recall from before, I could pretty much take something from down there, put it up here, make sure there's a comma and not the semicolon here. And I like to have uppercase name for parameters. And I compile, oops, I forgot. Case is important, so this has to now be uppercase UV. This is pure cosmetics, but I kind of like it. So now we have a UV input, and notice this one, because again, nothing changed. Look, another change that changed nothing. The UV gets a default value of this. So if we are not connecting anything to our brand new UV input that we just got here, it will use the point UV0, so the regular coordinate space. But now we can drop in a shader for UV channel, and we just happen to have another coordinate space in the scene. So coordinate space 2 looks like this. So now we can choose coordinate space, or we could say I want to do object space. Then of course I need to change the scale again to like 20 or something. There, now object space follows the object. Or I can even make it thus that I use the named coordinate space. UV goes in there, it's object, it's now world, so like this. I can do screen. Again, I have to adjust the scale because as we screen goes from 0 to 1. So there, now it's in screen space. You see it's stuck to the screen. I can choose the non-device coordinate one, which is kind of similar to screen, and I can choose raster. Again, of course, raster needs a different scale, so we say 20 will be pixels. You see, now we have a grid in pixels. This looks kind of neat. It looks like some kind of anime screen toning. We should swap these two colors actually. There we go. Kind of nice. I wish it was leaning in 45 degrees. Well, here's the reason why it's so cool to do this on inputs. Because I'm gonna drop in my UVW transform here and just say rotate this 45 degrees. And now we had made kind of an anime looking shader with green tone dots leaning in 45 degrees, and things are starting to get exciting, right? Well, that's where I'm going to leave you guys, because this is all for lesson number 2. Tune in next time for more fun stuff about coordinate spaces and nerdy stuff, and then maybe taking our thing to do something slightly more visually exciting. I hope you enjoyed this lesson number 2. Zap out. Bye bye.